Hello everyone. In this video I'm going to be covering the topic of atomic structure from the AS-Level AQA Chemistry syllabus. Please note that it is AQA syllabus and some of the things that I may be talking in this video are not applicable to all exam boards. However, if you need a general understanding of this topic, please feel free to watch. And let's begin. What we currently picture when someone says an atom is different to what people thought of an atom 100 and 200 years ago. This is because the structure of the atom evolved over time, leading to the development of different atomic models. The first model and the very idea of the atom originated in ancient Greece with a philosopher named Democritus, who came up with this idea through a thought experiment. Imagine you have a bar of pure gold. If you cut this bar in half, you will end up with two halves. Then, divide those halves again, and you get 4 quarters. The question is there a point at which you can no longer divide the material any further? Democritus theorized that there must be a smallest indivisible unit of matter, and he called this unit an atom, derived from the Greek word atomos, meaning indivisible. However, in the 19th century, with the advancements in chemistry, scientists started to question the philosophical nature of the atom and started asking for a more concrete definition. So, in 1803, an English chemist named John Dalton revolutionized the concept of the atom. He proposed that atoms are not all identical. Instead, there are different types of atoms with unique properties, which we now recognize as elements. Dalton also suggested that atoms can combine to form compounds, giving rise to the diversity of matter around us. At this point, atoms were thought to be fundamental and indivisible. However, this notion changed in 1897 when, through his famous cathode ray tube experiment, Sir Joseph John Thomson discovered the existence of electrons. In his experiment, Thomson applied a high voltage, which produced a beam of electrons. When he applied an electric field, these beams were deflected, indicating that the electrons carried a charge. It could not be atoms since they were believed to be neutral. As a result, Thomson proposed a new atomic model, often called the plum pudding model. In it, the atom was thought to consist of negatively charged electrons embedded within a positively charged pudding, resembling a dessert. In 1911, Ernest Rutherford challenged this model with his groundbreaking gold foil experiment. He directed alpha particles at a thin sheet of gold foil and tracked their trajectories. Most of the particles passed through the foil unaffected, which suggested that atoms are mostly empty space. Some particles were deflected, indicating the presence of positive charge within the atom. However, a few particles were reflected back entirely, leading Rutherford to conclude that atoms contain a small, dense, positively charged nucleus. This experiment gave rise to Rutherford's model of the atom, replacing the plum pudding model. However, some mysteries remained, such as the origin of spectral lines observed in atomic emissions. In 1913, Niels Bohr proposed a solution. He suggested that electrons do not move randomly within the atom, but instead occupy specific fixed orbits. Electrons could only exist in these orbits and not in between, which explained the spectral lines of hydrogen. This marked the beginning of the Bohr model of the atom. With the advent of quantum mechanics, the understanding of atoms deepened. In 1926, Erwin Schrödinger developed a quantum model of the atom, which remains the most widely accepted today. Finally, in 1932, James Chadwick discovered the neutron, completing our modern understanding of the atom's structure. Moving on, for the objective 3.111, you have to be familiar with the basic structure of the atom. An atom is made of a nucleus with protons and neutrons, orbited by electrons. You have to know the relative charge and relative mass of subatomic particles, which are shown in the table. A mass number, which is usually denoted by a letter A, is the total number of protons and neutrons in an atomic nucleus of an isotope of an element. An atomic number, which is usually denoted by a letter Z, is the number of protons in the nucleus of an atom of an element. These terms are important when it comes to ions and isotopes. An ion is an atom of an element with an electrical charge. They are produced when an atom loses or gains an electron from the valence shell. An example of an ion would be lithium plus. It is produced from an atom of lithium which lost an electron. And since it now has more protons than electrons, the charges are uneven, and the total charge on the atom is 1 plus. When drawing a diagram of an ion, do not forget to put brackets and a charge in order to indicate the presence of charge on an ion. Isotopes are defined as atoms of the same element but with different mass number. Isotopes of the same element have the same atomic number, aka the number of protons, but different numbers of neutrons in their nucleus. Isotopes of the same element have different physical properties, such as melting point, but their chemical properties remain the same due to the same number of valence electrons. An example of isotopes would be isotopes of hydrogen. There are 3 isotopes of hydrogen, and as you can see on the picture, they all have different numbers of neutrons in their nuclei. In order to name the isotope of an element, you need to say the name of the element first, followed by a mass number, for example hydrogen 1, hydrogen 2, and hydrogen 3. But some isotopes also have common names, such as deuterium, as for hydrogen 2, which is also used in fusion reactions. Also, some isotopes of the elements can be radioactive, like uranium-235, which is used in nuclear plants. Mass spectroscopy or spectrometry is a technique used to identify the elements and find the masses and abundance of isotopes in a sample. There are different types of mass spectrometers, but the one that you need to know for your exam is the time-of-flight spectrometer. It works by measuring the time it takes for sample atoms to pass through the spectrometer, and it works in multiple stages. The first stage is ionization. There are 2 types of ionization techniques. They are electrospray ionization and electron impact ionization. Electrospray ionization works by first dissolving the compound in a volatile solvent. Then, under high pressure, this mixture is sprayed through a thin nozzle connected to a high voltage, and this causes sample atoms to gain a proton from the solvent, thus producing atoms with 1 plus charge. The second type of ionization is electron impact ionization. It essentially involves bombarding sample atoms with high energy electrons, which causes these atoms to gain 1 plus charge. Second stage is acceleration. The electric field is used to accelerate charged particles towards itself. The important thing is that each particle has an identical kinetic energy, but lighter ions travel faster than heavier ones. Third stage is ion drift. Pretty much nothing happens there. Ions travel at constant speed throughout the tube, and from the previous stage we know that lighter ions travel at higher speeds than heavier ones. Fourth step is detection. So when ions reach the detector, they cause a potential difference and produce current, and the size of the current corresponds to the abundance of an isotope. So high current equals to high abundance of that particular type of isotope. Since each type of isotope arrive at different time, since they have different masses, the time it takes for the isotope to pass through the tube can be used to find its mass. And so from all of this data received from the spectrometer, scientists construct a mass spectra, which is a type of graph. Here is an example of a mass spectra. On the y-axis it has relative abundance, and on the x-axis it has m over z ratio. So m over z ratio is the mass number of an ion divided by its charge, and typically most of the ions have 1 plus charge. So m over z ratio simplifies to m. And so in the mass spectra of chlorine, there are 2 peaks because chlorine has 2 naturally occurring isotopes, which are chlorine-35 and chlorine-37. And so they have different heights because they have different relative abundances. Their heights will be in the ratio 3:1 because their relative abundances are 75 and 25%. And so in order to calculate the relative atomic mass of chlorine, you can use this formula, and when you substitute the data you get from the mass spectra, you get relative atomic mass of 35.5, which, if you have a look at your periodic table, is the relative atomic mass of chlorine. Here's an example of a more complicated mass spectra. This is a mass spectra of a molecule dodecane, which is a long-chain alkane molecule. And so, as you can see, when put into a mass spectrometer, dodecane produces lots of different peaks with different mass numbers. And this happens because During the ionization process, high energy electrons can break carbon-carbon bonds and produce what we call fragments, which are parts of a molecule with different mass numbers. And this process is random. We don't know which carbon-carbon bond is gonna break, so that's why lots of different peaks are produced. So, for example, this peak, the highest peak is called base peak, and it shows the most frequent fragment. So as you can see, it has mass number 57. So if you count the mass number of these molecules, probably this bond broke by a high energy electron and produced this fragment with 5 carbon molecules. And the most right peak is called molecular ion peak, and it corresponds to an unfragmented compound, which is dodecane. And so M over Z ratio corresponds to the MR of the molecule. So moving on from the mass spectrometry, we have electronic configuration. To begin with, try to picture an atom. And so typically, when we think of an atom, we think of something like this. We see that in textbooks, and it's not completely wrong. But this type of atom is the Bohr model of an atom. And if you remember from the first slide, after the Bohr model, there were several other types of models developed later. And in reality, an atom looks something like this. And this is a picture of an atom of hydrogen, with red being a region with high probability of finding an electron, and blue being the region with low probability. And in reality, we cannot precisely know the location of an electron. We can only estimate the most probable location, and this is why this type of atom is incorrect, because in this model, the trajectories of the electron are fully predictable and the location of the electron can be precisely estimated. But in reality, it cannot be. And so, an orbital is a region with high probability of finding an electron, and each orbital can only be occupied by 2 electrons. There are several types of orbitals, S, P, D, and F, and each orbital has a different shape. So for example, S orbital has a spherical shape, and there is only one type of S orbitals, and in total, S orbital can accommodate up to 2 electrons. P orbital has a dumbbell-like shape, and there are 3 types of P orbitals. And in total, P orbital can accommodate up to 6 electrons, because of the 3 types of P orbitals. There are also D and F orbitals, but they have much more complicated shapes, which you do not have to know for the exam. So D orbital can accommodate up to 10 electrons, and F orbital can accommodate up to 14. So principal quantum number, denoted by letter N, is the number which represents the energy level that an electron occupies. Principal quantum number is just a fancy way of saying energy level. So each energy level has different orbitals, and a subshell is a set of orbitals of the same type occupying the same energy level. For example, one S orbital is an S orbital occupying the first energy level. 3D orbital is a collection of 5 D orbitals occupying the third energy level, and 3D subshell can accommodate up to 10 electrons. So in the table, you can see the energy levels, subshells each energy level is made of, and the total number of electrons each energy level can hold. Also, an important thing is that each orbital has a different associated energy, with F orbital having the largest and S orbital having the smallest associated energy. Electronic configuration of an atom shows how electrons are distributed inside the atom, which subshells they occupy, and number of electrons in each subshell. In order to write an electronic configuration of an atom, you need to follow certain rules. First rule is the Aufbau principle, which states that electrons first fill subshells of the lowest available energy. And so, if you have a look at this table right here, it shows which subshells each energy level contains. So for example, first energy level has only one subshell, 1s. Second energy level has 2 subshells, 2s and 2p. And third energy level has 3 subshells, 3s, 3p, and 3d. According to the Aufbau principle, electrons first fill subshells of the lowest available energy. And so 1s has the lowest associated energy, so it is filled first, followed by 2s, then 2p, then 3s, 3p, and so on. And so the order of the associated energies is this: 1s, 2s, 2p, 3s, 3p for the first 5 subshells. Let's have a look at an example. Neutral sodium atom has 11 electrons, and so according to the Aufbau principle, electrons first fill subshells of the lowest available energy. And so subshell with the lowest associated energy is 1s. It can accommodate up to 2 electrons, so 2 electrons fill the 1s subshell with 9 electrons left. Then after 1s there is 2s. It can also accommodate up to 2 electrons, so 2 electrons fill the 2s subshell with 7 electrons left. After 2s there is 2p. It can accommodate up to 6 electrons, so 6 electrons fill the 2p subshell with 1 electron left. And after 2p there is 3s. It can accommodate up to 2 electrons, however we need to only accommodate 1, so 1 electron goes into 3s orbital with 0 electrons left. And so the overall electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. Another example is sulfur. Just like with sodium, we use the same principle in order to produce sulfur's electronic configuration. So 2 electrons go into 1s subshell, 2 electrons go into 2s subshell, 6 electrons go into 2p subshell, 2 electrons go into 3 subshell, 4 electrons go into 3p orbital with 0 electrons left. And so the overall configuration of sulfur is 1s2, 2s2, 2p6, 3s2, and 3p4. However, there are exceptions. If you look at this order of the associated energies with every subshell, 3s subshell is followed by 3p, and logically you would assume that the next subshell with the lowest associated energy is 3d, because it's the only unfilled subshell on the third energy level. But this is not what happens in the reality. The reality is that 4s subshell has a lower associated energy than 3d, so it is filled before. And so the new order of the associated energies is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. And so if you have a look at this example, calcium atom has 20 electrons, and as usual, 2 electrons go into 1s subshell, 2 electrons go into 2s subshell, 6 electrons go into 2p subshell, 2 electrons go into 3s subshell, 6 electrons go into 3p subshell, and we have 2 electrons left. And so if you have a look at this order, after 3p, 4s subshell is filled. And so 2 electrons go into 4s subshell and 0 electrons is left. And so the overall electronic configuration of calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Another example is vanadium. Vanadium has 23 electrons. So using this order of associated energies, we get 2 electrons in 1s, 2 electrons in 2s, 6 electrons in 2p, 2 electrons in 3s, 6 electrons in 3p, and we have 5 electrons left. After 3p, electrons go into 4s instead of 3d, but 4s can only accommodate 2 electrons. So 2 electrons in 4s, and we have 3 left. And 4s subshell is followed by 3d subshell, so 3d subshell can accommodate up to 6 electrons, but we only have 3, so 3 electrons in 3d subshell, and we have 0 left. And so the overall electronic configuration of vanadium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, and 4s2. Please notice that even though the 4s subshell was filled before the 3d, in the overall electronic configuration, they are arranged in the ascending order of the principal quantum number. But as always in chemistry, there are some exceptions. You might have noticed that d orbital has interesting behavior, in the way it does not behave as other orbitals. And one of the features of the d orbital is that it is the most stable when it is fully or half filled with electrons. And because of that, electronic configuration of copper and chromium are not what you think they are. Copper has 29 electrons, and instead of following the expected order, its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s1. At first glance, this might seem strange. Shouldn't the 4s subshell have 2 electrons before the 3d subshell starts filling? You're right. Normally, electrons fill the 4s subshell first, but in this case, having completely filled 3d subshell makes the atom more energetically favorable, so one electron shifts from the 4s to the 3d subshell. On the other hand, chromium, which has 24 electrons, has an electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. So, just like with copper, chromium is more energetically stable when its 3d subshell is half filled, and in order to achieve that, 4s gives up one electron. The good thing is that there are only two exceptions, copper and chromium, and other atoms follow the pattern I described earlier. You might have noticed that writing a full electronic configuration of an element takes a lot of time, and so in order to not write every subshell over and over again, chemists invented a shorthand electronic configuration. In its essence, shorthand electronic configuration works by taking a full electronic configuration of an element and replacing a part of it with an electronic configuration of a noble gas. For example, argon has 18 electrons and its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6. And zinc has an electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. And the shorthand electronic configuration of zinc would look like this: Ar in square brackets followed by 3d10 and 4s2, where Ar in square brackets assumes a full electronic configuration of argon. Another example is phosphorus, which has an electronic configuration 1s2, 2s2, 2p6, 3s2, and 3p3. And so the shorthand electronic configuration of phosphorus would look like this: He in brackets followed by 3s2 and 3p3, where He in brackets assumes the full electronic configuration of helium. Electronic configuration of argon in this situation cannot be used, since argon has more electrons than phosphorus. Another way to show an electronic configuration of an element is using electrons in-box diagram, or also called orbital diagram. The main idea behind this diagram is to show how electrons are arranged in each orbital of each subshell, with each electron represented by an arrow. This is where the other two rules of assigning an electronic configuration come in. The Hans rule tells us that electrons in the same subshell fill the orbital singly before pairing with other electrons. Common way to think about this rule is to think about seats on a bus. When people board a bus, they tend to sit alone, and only start to pair up once all the empty seats are filled. Same thing happens to electrons. Another rule is the Pauli exclusion principle, which states that electrons in the same orbital must have opposite spins. This is actually a more simplified version of the Pauli exclusion principle, and the actual principle is a bit different. But in the context of electrons, you have to know that except for charge, mass, and other properties, electrons also have a property called spin. You do not need to go into the details of what spin is. However, the main thing you have to know is that there are two types of spin, up and down. And when the electrons are in the same orbital, they must have opposite spins. Let's look at an example: copper. Copper has an electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s1. When filling the electrons in-box diagram with electrons, you follow the same rules as with subshell notation. The main rule is the Aufbau principle, which states that subshells with the lowest associated energy are filled first. So according to this rule, 2 electrons go into the 1s subshell, 2 electrons in the 2s subshell, 6 into p, 2 in 3s, 6 in 3p. Then, if you remember, 4s subshell is filled before 3d because it has a lower associated energy. You can actually see it on the diagram because 4s subshell is drawn below the 3d subshell, but since copper is an exception and has only 1 electron in the 4s subshell, 1 electron goes in, and 10 electrons go into the 3d subshell. As you can see, each orbital is represented by a square, and in each square, electrons are represented by arrows, which are pointing in opposite directions because of the Pauli exclusion principle. Another example is arsenic. For simplicity, when drawing an electron in box diagram, my advice would be to write a normal electronic configuration of an element first, before drawing electrons. So arsenic has an electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p3. As always, lowest energy subshells are filled first, and electrons in the same orbital have opposite spins. Now, if you have a look at the last subshell 4p, you see that electrons occupy the orbital singly before pairing up. This is an example of the Hans rule. From the mass spectrometry, you know that ionization in chemistry is the process during which an atom loses an electron. Therefore, first ionization energy is defined as the energy required to remove 1 mole of electrons from 1 mole of neutral atoms in the gaseous state under standard conditions in order to produce 1 mole of 1 plus ions. I am saying first ionization energy because after a neutral atom has been ionized to 1 plus atom, it can be further ionized to 2 plus and 3 plus ions, which require different energies. Therefore, first ionization energy is the energy required to convert neutral to 1 plus ions. Successive ionization means removal of more than 1 electron from the same atom. For example, second ionization energy is the energy required to remove 1 mole of electrons from 1 mole of 1 plus ions in the gaseous state to form 1 mole of 2 plus ions, also in gaseous state under standard conditions. There are several factors that affect ionization energy. They are nuclear charge, atomic radius, and shielding, which basically means the number of electron shells between the nucleus and the outer shell. Successive ionization energies increase as more electrons are removed. This happens because with each removed electron, atom gains more positive charge. And because of the increased positive charge, attraction between the nucleus and the outer electron is stronger, which in turn results in more energy required to remove further electrons. Now we are going to have a look at the trends in ionization energies across a period and a group. So down a group 2, ionization energy decreases, because as you go down the group, the number of electron shells increases, which results in more shielding. Also, as you go down the group, the atomic radius of the atoms increases. This results in less attraction between the nucleus and the outer electron, which leads to smaller ionization energies. If you remember, elements in the same period all have the same number of electron shells. And so, across the period 3, ionization energy generally increases. This happens because the number of protons in the nucleus increases with each element. However, shielding and atomic radius remain relatively the same because of the same number of electron shells. This results in more attraction between the nucleus and the outer electrons, which results in higher ionization energy. However, there are two exceptions. If you have a look at the graph, the general trend is that the ionization energy increases across the group. But it does not seem to happen for aluminium and sulfur, whose ionization energies decrease compared to the element before them. In order to understand why it happens, you need to understand their electronic configurations. Aluminium's electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p1, and the element before aluminium is magnesium, with an electronic configuration 1s2, 2s2, 2p6, 3s2. In the case of aluminium, electron is being removed from 3p subshell, while in magnesium, electron is removed from 3s subshell. 3p subshell has a higher associated energy than 3s subshell, so electron in it has more energy. Also, 3p subshell is located farther away from the nucleus than 3s subshell. And finally, 3p subshell experiences additional shielding provided by 3s subshell. This results in less attraction between an outer electron and the nucleus in aluminium compared to magnesium. Therefore, aluminium has lower ionization energy than magnesium. In the case of sulfur, it is even simpler. If you have a look at the sulfur's electron in box diagram, electron is being removed from the 3p subshell, from an orbital with 2 electrons in it, compared to phosphorus, where electron is removed from an orbital with only 1 electron in it. This additional electron repulses the electron being removed, which makes it easier to remove an electron in sulfur than in phosphorus. Therefore, sulfur has a lower ionization energy than phosphorus. This is the end of the topic of atomic structure from the AS-Level AQA Chemistry syllabus. If you want to use this presentation for your revision, you can find it in the description of this video for free. Next topic will be amount of substance. See you next time.